Okay, so myself, Amit Pathak, I'm from uh, Varanasi, Banaras University, Varanasi. I work in the Department of Physics, and mostly my research area is interstellar dust and molecules. So today I'll be talking about, I'm giving two lectures today and tomorrow. So today I'll be talking about broad aspects of the interstellar medium, and I'll try to give some examples to explain. And mostly I'll be using spectroscopy to, how spectroscopy can be used to understand the interstellar medium and its materials and properties, etc. So interstellar medium is, uh, as we understand, it is the space between stars. Okay, and that space was thought earlier, very early, 1900s, was thought that that space is empty and there's nothing in that space. And there were some proofs as well. I mean, people were looking using the old generation telescopes. They were looking at stars and they were seeing the stars. But between two stars, they found that it's a black area and nothing is coming out of it. And mostly people were using visible, the visible part of the electromagnetic spectrum. So the telescope technology was not so developed as of currently. So I'll be starting with some basics. You already know about the Planck's equation and the Weier's. Now Planck's equation helps us to, we can draw this black body curve, and then we can find the temperature of a particular object, which is the radiation from that particular object is coming because of its temperature. So it's basically thermal radiation. Like our body gives some radiation because we also have a temperature. Okay, so that is basically black body radiation. So black body radiation is mostly used to determine the temperature of, for example, objects like stars. No. But we can use black body curve even to get the temperature of the material, mostly solid particles in the interstellar space, interstellar medium. So that is why black body curve is important. So this is the black body curve. Everybody knows about this. So we have a cooler object, we have hotter objects. We can see the as we go from cooler to hotter objects, the the peak is shifting towards lower wavelength, and the area under this curve is also increasing. So this is a general idea of the black body curve. So now coming to spectroscopy. Can I come down? Because I'm finding it difficult to see this. I think he has to. Sure. Huh? Is it all right? Yeah. Okay. So some basics about spectroscopy. So spectroscopy. So we can get a spectral line. So spectral line. How do we get any spectral line? We get spectral lines from atoms. We get spectral lines from molecules. So what exactly is happening? The electron, which is in the ground state, is actually going to the excited state, or the electron which is in the excited state is coming down. So we get absorption lines, we get emission lines, and that absorption or emission, the spectral line is telling us about the material, the atom or the molecule actually. Okay. So it tells us whether this transition is taking place in a neutral atom or an ionized atom. So we also get to know about the physical property where that atom is present. Because if it's ionized, so that means that particular environment is hot. So that is why it is hot. It is so photons are larger in number in that particular environment, which are ionizing the atom. Okay, and if it is neutral, then mostly it is benign type of environment. It's cooler environment. So we have two type of spectral lines, emission lines and absorption lines. So this is what happens. We have photons coming from some source. That source may be stars, and we have an absorbing material, which may be the material in the interstellar space. So this material will absorb some of the photons. It is not going to absorb everything. So because the transition takes place from one energy level to the other energy level, and that particular the difference, the delta E is fixed. So if delta E is fixed, then lambda or nu, the wavelength or the frequency of the transition line is fixed. Okay, so that particular photon will be absorbed. So what we start seeing is, we see that we are getting most of the light again here. The detector is receiving most of the light, but some of the lines are missing. So the black lines which you see have been absorbed by the material in this interstellar cloud. Okay. So this tells us about the absorbing material. So these are basically absorption lines. So we can have absorption lines like here. So this is the whole thing is background, and we have absorption lines, and we can have emission lines. So emission lines. So there is no background actually, and we see emission lines. So the basic difference when we are trying to measure the absorption or the emission lines is, for absorption we need to have a background source. So something like, we have a source, we have material, we have detector. So source and detector, and the material is absorbing, and we get absorption spectra. For the emission line, we don't need the background source. So if the material has absorbed, so the electrons are now in excited state, and they have to come down to the ground state. Okay, so they will come down, because initially they are going to, because nothing is going to, stay in the excited state. They are unstable. So the electrons actually come down to the ground state. When they are coming down to the ground state, it emits. The material emits. So the emission photons goes everywhere. The material is here, and the emission photon is going everywhere, in all the directions. Our detector is here, which is mostly measuring the absorption lines, because we have a background. The emission photon which goes in this direction, direction of the detector, which is measuring the absorption line, is also collecting the background. Okay. Now the background is so strong that the emission photons become very weak, so it is not able to collect. It only gets the information about absorption. It is not going to give us any information about emission. Everybody got this point, right? Okay. So now if we have to measure the emission, we have to go in a direction where there is no background. So we shift the detector, because the emission photons are being emitted in all the directions. So we shift the detector, and because the emission photons are being emitted in all the directions, so the number of photons coming to a particular direction will be small. The absorption was only in one direction, so the absorption lines are strong. The emission lines will be weaker, because the photons are going everywhere. So if we keep the detector here, it will collect some emission photons without the background. So now we get the emission spectra. So we can collect the absorption spectra, we can collect the emission spectra. But that is not in our control, because when we have a telescope and we are looking towards towards space, so if we have a star in the background, so that star will act as a source, and the intermediate material is absorbing. Okay, so we will always get absorption spectra. So in order to get emission spectra, we'll have to point our telescope where there are no sources. No? We don't have any source in the background. There are no stars. So we are looking where? We are looking only towards the interstellar material, which will emit. So then we can capture the emission spectra. So this is, you can see, this is a spectrum of G5 sun-like star. You can see the black body curve kind of thing. And we have absorption lines. So we are looking at the star, and we are capturing absorption lines. These absorption lines are not due to the interstellar material. These absorption lines are due to the material which is present in the atmosphere of the star itself. Okay. So you can see all these absorption lines. And if you know the wavelength, because there are a lot of labs which measure these kind of spectra for atoms and molecules, and there are databases like NIST in US, and there are several others. So they have a record that the absorption or emission line of this particular atom will fall at this particular rate. So you can match this. You can try to match the absorption line to that particular atom. Then you know that, okay, this absorption line is due to atom X. This absorption line is due to atom A. Okay. So in this way, yeah.
Sir, how do we understand that these absorption lines are from the atmosphere of the star and not from?
Yeah, I will tell you. I'll tell you about that. Yeah, in the coming slides, I'll show you. This is a very good question actually. So this is coming from the star. Just believe me, I'll tell you later on. And then you can know about the materials. For example, sun is also known as helios. So helium was first detected in the sun. Later on, it was detected on the Earth. So in this way, we get to know about new atoms and molecules and ions. The interstellar space. I will tell you about the physical properties, and you will be surprised to see that it is so rare. It is very rare, and the density is so less. So some basics again. So we can have the lines can have redshift or blue shift. Okay, so redshift means that the lines are going, the absorber is going away from us. Blue shift means the absorber is coming towards us. And we also can have broadening. So there are several processes which broaden the spectral lines. So everybody already knows that all the spectral lines will have a natural line width, which is due to the uncertainty principle. The Heisenberg uncertainty principle will allows always any kind of line to have some, because the electron goes into the excited state and it stays there for some time. Okay, so that actually creates this natural line. And then we can have broadening because of Doppler broadening. So Doppler broadening is because of the temperature. So the atoms are moving in a zigzag manner, the absorbing atoms. So that will actually broaden the lines. Then we can have collisional broadening. When the density of the atoms in the absorbing material is higher, when we have a lot of atoms, then they will collide with each other, and there will be motions towards the detector or away from the detector. So then we will have collisional broadening. Then we can have splitting. LS coupling and all those kind of things, which, like for example, sodium D lines. So we can have splittings and the natural line width I've already told about. So how does the interstellar medium come into existence? So just after the Big Bang, it was mostly hydrogen and helium. So whatever, there were no stars. So everything you can call as, interstellar medium. There was no stars, so nothing, no interstellar medium. But then when the first stars were born, and so what happens? The star was born, and then it evolves, and then we have a mass loss from the star itself. Okay, so sun-like star, after say approximately 5 billion years, it will shed away its envelope, and the envelope goes into interstellar space. So that envelope contains all kind of materials which sun has. The photosphere of sun, the atmosphere of sun has all kind of material, including hydrogen, helium, and several other atoms and ions. So all those atoms and all that material goes into interstellar space. When it goes into interstellar space, it becomes the part of the interstellar space. Okay, so in interstellar space, we can have several kinds of clouds and phases. I will talk about it. So so whatever is in the interstellar medium was earlier part of the star. Okay, so and when the star evolved, whether it forms a white dwarf or a black hole or a neutron star, everything, it goes through an evolutionary process where it sheds away its envelope. Okay, so by becoming a red giant kind of thing, or even through supernova explosion. So sun-like stars, all the lighter elements are from low mass, the evolution of low mass stars, and the heavier elements, because once this star is very massive, it goes through a process and it forms a supernova explosion. The core, it creates a lot of material. It creates even higher elements. The heavier metals are created inside stars. So it can create up to iron. So all those material will be again going into interstellar space when a supernova explosion occurs. So lighter elements come from less massive stars. The heavier elements come from more massive stars. And during supernova explosion, even more heavier elements are being formed, and they all are going into interstellar space. So this becomes a cycle. When it becomes part of the interstellar space, and then it becomes I mean, if the density grows and there is a disturbance, the equilibrium is disturbed, and then again a gravitational collapse can happen, and it can lead to formation of a newer star. Okay, so this is a cycle from star to interstellar space, again formation of stars and planets. So it becomes a cycle known as cosmic cycle. So how do we know that interstellar space has some material? It actually has some material and things can exist there. So first evidence came into 1930s when by the detection of calcium through H and K lines and sodium doublet lines. So you can, if you read the second statement, it says narrow stationary lines with respect to the Doppler shifted stellar lines were found. So stars are moving, and especially if we have a binary object, the best way to understand if there is material in the interstellar space is to have a binary object in the background. When we have a binary object, because if we have a two-star system, it is going around each other, something like this. So the stars are continuously moving. When the stars are continuously moving, the lines, the absorption lines due to the stars will show red shift or blue shift. It is coming towards us or going away from us. So it will always be showing red. So those particular lines will be either red shifted or blue shifted. But the lines, because of the material present in the interstellar space, that is not moving. So that will be stationary. So this gives your answer. So then we can recognize whether this is coming from the star or it is coming from the material which is in the interstellar space. So there was a scientist, Robert Trumpler. So in 1930, what he did was he started looking and doing measurements of star clusters. So he was looking at star clusters. So star clusters you already must have. So star clusters are basically gravitationally bound stellar systems. A lot of stars are there. So he was looking at star clusters, several of them. And then what he was doing, he was trying to get the distribution of stars in the star cluster. So if we have a star cluster A and we have another star cluster B, and the approximate number of stars and the distribution of stars in cluster A and cluster B is almost similar. Okay, so the size of the cluster will almost be similar. Okay, so we have like twin. We have cluster A and cluster B, which acts like twin. Now, if cluster A is nearer to us and cluster B is further away from us, then we can, if we know the distance to cluster A, then we can try to calculate or estimate the distance to cluster B. Okay, because the light, the angular diameter of the cluster will reduce. When we look things which are closer to us, we find that those things look larger, and the same thing moves away from us, it becomes smaller. Simple funda. So in this way, he was measuring the angular diameter and estimating the sizes. And he was measuring he also measured the photometric distances. So photometric distances means if we have say star 1 and star 1 is in cluster A, okay, and there is another star 2, which is similar to star 1. So star 2, but star 2 is in cluster B. Okay. So then the light coming from star number 1, the light coming from star number 2, because they are same, say they both are G-type stars. So the amount of photons and the particular wavelength and all will be similar in nature. Okay. So then we can also get an estimate of the distance using this photometry. Okay. So suppose, for example, I am looking at this tube light, which is nearer to me, and then I can look at that tube light, which is further away from me. Okay. So this tube light, I'll get more photons, and from that tube light, I'll get lesser number of photons. It follows the 1 over r square law. Okay. So it reduces. So then you can get an estimate. So if you know the distance to this tube light and you are receiving n number of photons, so you can calculate approximately, you can measure the number of photons coming from that tube light and approximate the distance to that tube light. Okay, so then now he got two ways of estimating the distances. One was the angular diameter of the cluster, and the other was the photometric way of determining the distance to the cluster. Okay, what he found was the apparent angular diameter distances were smaller than photometric distances. So he measured the angular diameter and he found that okay, distance to cluster A is say 5 kilometers and distance to cluster B is say 10 kilometers. Now he measured the photometric distance of cluster A and he found that it is okay 5 kilometers, but this one is not 10 kilometers. This is say 12 kilometers. Using photometry, he found that it is 12 kilometers. So, so it was contradictory. Okay, it was not, it was not matching. Both the methods were not matching. Why it was not matching? Because the photometric distances relied on the number of photons reaching your telescope. Okay. Now, if there is some material in between the telescope and that particular cluster, that material will absorb some of the photons. Okay, and then what will happen? The number of photons that you are getting will be reduced. If the number of photon is reduced, then you will say, oh, the distance is further away. Okay, everybody understands this. So this mismatch between the angular distance and the photometric distance actually instigated him to say that there was some material present in the interstellar space. And when we go on measuring larger distances, the material also will become large. The amount of material that is absorbing the photons will increase. Okay, so photometric distances always will be smaller. So this actually confirmed, for the first time, this confirmed the presence of material in interstellar space. Okay, and then then this binary thing was there, where if you have a binary star, then you can confirm the stationary lines belong to the interstellar space and moving lines belong to the stars. So that also confirmed. Later on, that also confirmed the findings of Crumpler, and so it was generally taken. I mean, scientists actually accepted the fact that interstellar space existed and it had its own physical properties, and played a very important role in formation of new stars and planets, evolution of galaxies, and so on. So it played a very important role, and scientists were interested in studying. For the first time, they got interested in studying the material present in space. So this is components or phases of ISM. So once we know that ISM exists, now we can define what phases and how many divisions we can make in the Islam media. So these are the components: molecular clouds, neutral medium, warm neutral medium, ionized medium, H2 regions, and hot ionized region. So molecular clouds are dense clouds where molecules can survive. So interstellar space will be heavily bombarded by photons coming from stars. Okay, and these photons can destroy. I mean, these photons will vary from say X-ray, UV, and all longer wavelengths. So the more energetic photons will break the molecular bonds, and mostly the material present in interstellar space will be atomic in nature or ionized in nature. Okay, but then if you can protect the material, so if you have a shielding, okay, so that shielding can protect the material, and then molecules will be able to survive. And we have confirmation that even very large molecules, for example, fullerenes, if you know, fullerenes are C60, only carbon, 60 carbon atoms, they create a football kind of molecule. That molecule has already been detected in interstellar space. Okay, so it actually tells us that even such large molecules can survive. So we have molecular clouds where the density is quite large and temperature is very low. Okay, so but this density, you can see, you compare this density, all these densities that I've noted here, if you compare it with the density on the Earth, for example. So in 1 cc, how many atoms should be there on Earth? Roughly, any idea? Huh? 10 to the 23. Avogadro's, comparable to Avogadro's number. And there you can see that it is 10 to the 6, which is 17, 16, 17, 15 orders of magnitude less than what we have on Earth. And any kind of vacuum system you build on Earth, you cannot go to such kind of vacuum. Forget about all these. You cannot go to this, the tensest part in the interstellar space. You cannot create, you cannot replicate it on Earth. It's very difficult to replicate. So that is why studying, so in order to imitate the properties of interstellar space in a lab on Earth is extremely difficult. But people have tried, at least temperature wise, scientists have gone to very low temperatures, but density wise, it is quite difficult. Then we have cold neutral medium, which is the density is less, temperature will be higher. So if we go down, the temperature keeps increasing and the density it becomes rarer and rarer. H2 regions are dense because H2 regions are the regions which are in the vicinity of uh, young massive stars. They are dense because the star is just formed. So and it is formed from a dense cloud, interstellar cloud. So the density in the vicinity of that star will be higher. The temperature also will be higher because it is a young massive star. It is giving out a lot of UV photons which are ionizing the hydrogen in the vicinity. So that is why. So H2, everybody understand when I say H2 means H plus. Okay. And how do we observe these? So we can use different parts of the electromagnetic spectrum to observe on this. So we can have radio or infrared to detect molecules in the molecular clouds. The cold and warm neutral medium, basically, we can detect using the 21 centimeter absorption line of hydrogen, again radio. Then H alpha emission can detect the warm ionized medium and H2 regions. And the hot ionized medium will be detected using X-ray and UV astronomy. Okay. So again, coming to, so I've already told you about this. So molecular clouds, we have mostly molecules will be there. So how do we detect these molecules? Detecting H2 will be difficult. So we can trace the molecular clouds using CO. Why CO? Why not H2? Anybody? Yeah. So CO has dipole. So it has dipole, so it will have rotational spectra, and you can utilize the rotational spectra. You can detect it using microwave spectroscopy. That is easier to detect. So once you detect carbon monoxide, then you can say that okay, this is a molecular cloud because molecules can exist there. And then we can have H1 absorption and H1 emission, 21 centimeter line. Using that, you can detect the cold neutral medium and warm neutral medium. Ionized mediums will be detected by H alpha line, 660 angstrom V. And hot ionized medium will be detected using X-ray. So there are intermediates between the phases. We have warm ionized medium, we have hot ionized medium. We also can have warm hot ionized. So in the end, towards the end, I'll give you an example where we did some study of O6 ion, which actually detects the warm hot wave, warm hot ionized. Okay, so you can detect different ionized, different kind of ionization of a similar atom, for example, O. So we can have O1, O2, O3, O4, O5, and it will tell us about different physical properties, different environments of the interstellar space. So interstellar clouds, so we can have molecular clouds. Basically, we have three basic clouds: the dense molecular clouds, diffuse clouds, and in between these two, we have translucent clouds. Yeah, so we have diffuse atomic, we have diffuse molecular, translucent, and dense molecular cloud. Okay, so this is a very nice review article published in as I think reviews, annual reviews of astronomy and astrophysics. So you can see the various physical properties of the temperature is so low here and the temperature keeps increasing. Diffuse is exposed. It is diffuse, sparse. So the photons can reach there. But then as we go from diffuse, so we have a star, we will have H2 region, and when we go away from the star, we'll have diffuse cloud, translucent cloud, and molecular clouds. So this diffuse and translucent cloud actually acts as shielding to the molecular cloud. They can absorb all the photons. So diffuse cloud will absorb, and we will have ions in the diffuse clouds. That photons which are passing through the diffuse clouds are used in ionizing the atoms and material there, and they will not be able to reach the molecular cloud. So the molecular cloud is safe, and the molecules are safe, and molecules exist actually. The existence of molecule is very, very important. So in tomorrow's lecture, I'll be talking mostly about dust and molecules, where I will tell you that most of the molecules that have been detected are organic in nature, carbon based, and the life on Earth is also carbon based. So there might be a link. So again, the physical properties, how the various ions and atoms vary in different clouds. So we have diffuse atomic where the hydrogen, and then it goes down. Hydrogen goes down as we go from rare clouds to dense clouds, because it is getting converted to hydrogen molecule. Okay, in similar fashion, we have iron here, the diffuse cloud, because it is exposed to UV photons coming from stars, and then these ions are getting converted to neutral atoms, and then they get converted to molecules as we go from diffuse to dense clouds. So H2 regions, I've already told that these are ionized hydrogen regions in the vicinity of young massive stars. They can be detected using H alpha emission, the H alpha, the Palmer line hydrogen, and they tell us about. I'm going a little bit fast because so they actually, if you detect an H2 region, then you can predict that star formation activity is going on. So it is like a precursor to the, we have giant molecular cloud, and then it leads to star formation, and star formation activity is going on. Then only the formation of H2 takes place, and we can, it is so lot of, because it is very close to the young massive star, so it is already heavily exposed to the UV photons coming from the stars. That is why it is ionized. So this is, you can see, this is what is happening. So we have young stars giving away a lot of photons, and these photons come and strike ionize the hydrogen. So hydrogen is ionized in the H2 region, and what happens is the ionized hydrogen recombines with the electron, and it recombines with the electron. The recombination leads to formation of again hydrogen atom, but that hydrogen atom is not in the ground state; it is in the excited state, and then it can lead to when from the second excited state to the first excited state leads to the emission of H alpha photons, which are red in color. So detection of this tells us that. So if we are detecting H alpha emission, it doesn't tell us that. Actually, it is indicating the presence of ionized hydrogen. It is coming from neutral hydrogen, but it is telling us about ionized hydrogen. Okay, this is an important point. So this is what is happening actually. So most of the photons, because we need 13.6 electron volt or higher to ionize the hydrogen. So most of these kind of photons are absorbed in the H2 region itself. They, rarely escape. Heating and so interstellar space, because it is getting a lot of energy, a lot of photons. So it will be heated up and it will be cooling. So there is it is not in thermodynamic equilibrium. It is never in thermodynamic equilibrium. This heating and cooling process is a continuous process which is going on forever. And there are we can so heating means what? Heating means you're adding temperature or energy to the system. That means if something gets more energy and it travels faster, then the system becomes hot. And if it loses the energy and starts moving slowly, then it becomes cool. So in this process, this is the way to define heating and cooling of the material in the interstellar space. So heating can take place by these processes: photoionization, emission by cosmic rays, photoelectric effect, molecular hydrogen formation on grains, shock heating and cooling takes place by giving away radiation. So if something is excited, and then it comes down by giving away radiation. So when the radiation escapes, the material is cooled down. Then we can have free emission of electrons and dust emission collision. So photoannihilation means what? Photoannihilation means photon comes, hits an atom, the atom is converted to an ion, the electron is released with some energy. This electron is moving some energy, it higher some speed. So the medium becomes hot. So this is one process of heating of. But when it recombines, for example, the H alpha emission, we saw that H plus ion is recombined with the electron. Then the recombination will lead to cooling of the ions because it will recombine and it will radiate some amount of energy, and then it will lead to. But this ionization process leads to, because the ion will be moving at some speed, the electron will be moving at some speed, so it will result in heating of the ions. Cosmic rays can come and hit material present and ionize it, and then again it imparts energy to this material, this atom. So then it results in the heating of the ions. UV photons can ionize a grain surface. Grains are basically solid particles. So UV photons can come and hit the grain surface, the grains, and the grains can release an electron, and then again it gains energy. The medium gains energy because of the moving electrons. Then hydrogen formation. I'll talk about it more tomorrow. So two hydrogen atoms. So molecular hydrogen formation mostly takes place on the surfaces of grains. Okay. So two hydrogen atoms can get absorbed on the grain surface. They can move on the grain surface. They can combine, and they can be released. Because when they combine, they will produce excessive heat. Okay? And the hydrogen molecule that is being released is moving at some it already has some energy. So it is moving in the ISN and it creates heating of the ISN. Cooling can be when collisions between electrons. So electrons and ion recombination basically. And recombination leads to the release of certain photons, and that results in cooling of the ISM. So cooling, you can see, this is what I've already told, the Balmer line. And free electron emission means electron is free, it is moving at some speed, and it comes close to some negatively charged system, and then it loses speed. Okay, it is like applying brakes to your vehicle. It loses speed. And when it is losing speed, because of the acceleration or deceleration of a charged particle leads to emission, continuous emission. So that continuous emission actually leads to the cooling of the ice. Dust emission. So when, say, a dust particle gets heated up, so when dust particle gets heated up, it can release, so it will emit in the IR, far IR kind of thing. Because the temperature of the dust particle is say 100 Kelvin, 200 Kelvin, or something like that. So it will start emitting. It will be similar to black body radiation. So the black body radiation can help in determining the temperature of the dust, which is present in the ISM. Because so we can plot a black body curve kind of thing for the dust particle, for the space interstellar environment where these dust particles are present, and then we can know about the temperature of the dust particle because it is releasing energy, so it is resulting in the cooling of the ice. Now I come to some technique where we can measure the column density of the absorbing material. So what is column density? So if you have a telescope and you are observing in a particular direction, so you can extend the telescope like column to the interstellar space, and the number of absorbing particles per unit volume present in that column is known as column density. So it tells you about the total number of absorbing material present. It gives you an idea of the total number of absorbing material present in that particular column. So this column, I mean, we are extending the column from the telescope to the interstellar space, but most of the material is there. Here, near to the telescope, there's nothing. So we get an idea of the density of the absorbing material present in the interstellar space. Okay. So how do we do that? We do this using some spectroscopy. So we define few things and then I'll show you how to measure the. This is a very old way of measuring column density. So this definition I've already given. We have some material present in the absorbing media, and we can integrate that material for the whole cloud. Okay, and then we get the total material that is absorbing, and that is known as column density. It is measured in units of per cc. Optical depth. Everybody knows what is optical depth. So if we have a photon, it goes in some media, it can penetrate up to a certain distance, and the penetration goes down exponentially. So that particular factor is known as optical depth. So optical depth can be defined like this. This is absorption cross section. I lambda 0 is the, suppose we have an object, a source, and then we have media, we have detector. So this will emit some photons, which will be I lambda 0. Intensity will be I lambda 0. After the photons get absorbed, whatever the detector receives is I lambda, which is always less than I lambda 0. And that goes down exponentially as it travels through the media because of the optical depth. Then we define equivalent width. So what is equivalent width? Equivalent width is something like this. So we have a spectral line like this. Okay, we can create an imaginary rectangle which has the same area as that of the spectral line. Okay, and the width of this imaginary rectangle is known as equivalent width. Okay, so this is the definition of equivalent width. Mathematically, we can calculate it like this. The difference between the photons that are coming towards the media, absorbing media, and which are leaving the absorbing media divided by the original number of photons gives you the equivalent width. Okay. Now, how this equivalent width changes as we increase the number of atoms or molecules in the absorbing media, how this equivalent width changes. Okay, so what happens is when the optical depth is less, when we have an optically thin environment where the optical depth is say like 1, 2, less than 1, something like that. So those are optically thin environments. So in optically thin environments, the number of absorbing atoms, molecules is less. So the equivalent width is linearly proportional to the number of atoms. Okay, we can see. So if we have, this is our spectral line kind of thing. Okay, this is normalized. I'll show you how to normalize this. But, so this is normalized. Now, if we double the number of absorbing, okay, later on, and we can have broadening. Okay. So in optically thin environments, we have Doppler broadening. In optically thick environments, we have collisional broadening. So optically thick environment means that the number of material, the number of atoms that are absorbing are large. So they will undergo collision among themselves, and it will lead to collisional broadening. The optically thin environment will have Doppler broadening. So because the number is less, so we'll have Doppler broadening. So in the optically thin environment, we see that yes, that if we double the number of absorbing atoms, then this optical depth, this is basically optical depth, it keeps increasing, keeps doubling. So the area under the curve is doubling. The equivalent width, if we try to find the equivalent width for this, we find that the equivalent width corresponding to the red one will be half of the green one. The green one will be half of the blue one. The blue one will be half of this pink one, purple one. Okay, so basically the equivalent width is following a linear kind of, you know, but this happens only in case of optically thin lines. So there is a linear relationship between number of atoms and equivalent width for optically thin lines. Okay, but when we start having optically thick lines, okay, so when the optical depth is 5 or higher, approximately 5 or higher, we call that optically thick environment. Okay, so in optically thick environment, what happens is you see that this particular line is like saturated. It is saturated. When it is saturated, then the equivalent width is not increasing as the number in the same proportion. It is not linear now. So the increase in equivalent width slows down. As we increase the number of absorbing particles, the equivalent width, the increase in equivalent width slows down. Okay. So when it slows down, that means now when the environment becomes optically thick, it is not following the same linear pattern. Okay.
So,
Yes.
so how do we know which broadening is present?
Yeah. So see, optically thick environment, the broadening will be, so you can see, I mean, I'll show you this optically thick environment, we know that the broadening will be because of collisions. Optically thin environment, we know that it is mostly Doppler broadening. But then you can see this, the variation in the lines, the optical depth variation, and then you can determine by the wings. So I'll show you an example. So we have very optically thick environment, and we see that it follows a very different way. Okay, so what actually is happening? So optical depth follows three kind of patterns: the equivalent width versus, if we try to plot equivalent width versus n column density, we see that follows three different kind of. So initially it was linear, and then it follows a different pattern. And if we further increase the amount of absorbing material, it follows a different pattern. So there are three different patterns which we see. Okay, here. So here is the answer to your question. So you can see that you can see the difference in the weights of the optical depth. The optical depth is plotted here. So you can see the difference in the weights. So when we earlier it was when we go for optically thin arrangement, then it was doubling. It was following a linear pattern. When we go to saturated stuff, the wings show slight increase. You can see there is a slight increase. But when we increase it to very high level, okay, then what we see is that the optical depth, the wings of this particular optical depth are increasing. Okay, so then again it start increasing at a higher pace. So earlier it was following a linear pattern. Linear pattern means it was as you double it, the equivalent width gets double. Then it gets, after it gets saturated, there won't be any increase in this length. There will be increase in the width, and the increase in the width is a very slow kind of phenomenon. Okay, and when we go to very high optical depth, very high number of optical depth, very large number of absorbing particles, then the wings increase at a faster pace. So this is what it shows. So this particular effect is Doppler broadening, and when the wings increase at faster pace, this is collisional broadening. Okay, so we can have Doppler broadening when we have optically thin environment, and so we can determine it from plotting the optical depth. So these three kind of patterns we see. We have a linear relationship between equivalent width and the number column density. And this, in the second pattern, we see that it follows the square root of natural log. So first we take natural log of the column density. That means we have slowed down the process. Natural log means 2 exponential power something. Okay, so we have slowed down the process, and then we are taking the square root, further slowing it down. Okay, and in the third one, when it is very large number, then again the pace is higher. Then the equivalent it follows square root of n kind of pattern. Okay, so this is the fastest, this is second fastest, and this is the slowest. Okay, So if we plot it, it looks something like this. So here we have equivalent width, and here we have column density. So this particular pattern optically thin, where it is linear, then it is square root of natural log, and then again the base increases and square root of column density here. So we can plot the equivalent width against column density, and then we can use this plot to calculate the column density. Because equivalent width we can measure for any spectral line, we can measure the optical depth and we can measure the equivalent width. Okay. Once we measure the equivalent width, we know where on this y-axis where do we lie, which point, and corresponding point we can calculate the column density. Okay, we can calculate the column density, and in this fashion, in this way, we can calculate actually the column density of the absorbing media, the absorbing particles. Okay, so these are the steps actually. So we have vertical axis, which is equivalent width. This is column density times F. F. You can see here we have F. F is the oscillator strength. So oscillator strength is something related to the transition that is happening. Transition that gives rise to the absorption line. Okay. So oscillator strength actually tells us the probability of that particular transition to happen. The oscillator strength. So oscillator strength can vary from 0 to 1. 1 is the highest, that means 100% probability. 0 means there's no chance of that particular thing. But 0.1, 0.2 are good numbers. That means there is a high chance of that particular transition to take place. So oscillator strength is related to a particular line, absorption line. So oscillator strength for sodium doublet lines will be different compared to alpha absorption line and so on. So then you can actually calculate. Okay. So, but here you can calculate what? You can calculate, you have to use once, because suppose we are doing it for Balmer alpha line. So Balmer alpha line tells you about the transition which is from the second excited state to the first excited state. Okay, for a neutral hydrogen atom. But we know that it was not neutral. It was H plus which recombined with an electron, and that recombined now hydrogen atom is in excited state and it comes down to the ground state following this path and it is releasing H alpha photons. So this gives you an idea of the neutral hydrogen atom, but we also have to get idea of the ionized hydrogen. And that idea we can get from the ISSAA ionization equation, which gives you the partition function of how the energies are being partitioned between neutral and ionized hydrogen atom. So you get an idea of the ionized hydrogen, number of ionized hydrogen. Okay, so you get an idea of, now you get the number, column density of neutral hydrogen atom and the ionized hydrogen atom. You can add it up and you get the total column density, which is responsible for the emission or absorption of H alpha line. Okay. I've already told you about the oscillator strength. So you can use this, I've already told. You can read the values. First you measure the equivalent width from the line, you plot the optical depth, measure the equivalent width, then corresponding column density, use the ISSAA equation, and then you compute the total column density of the atoms that are responsible for that particular line. Okay. So using this, we have done some work. It was published in 2011. So what we did was, this is the Large Magellanic Cloud. Okay, this is the Large Magellanic Cloud, and we use a telescope known as FUSE, Far Ultraviolet Spectroscopic Explorer, and we measured what? We measured the column density of O6 ion. Okay, so this is already told. Yeah. So this is the FUSE spectrum. So FUSE actually measures the far UV, the very far UV, and we get something like this kind of spectrum. So we have a background source, and you are looking. So that background source is now in the Large Magellanic Cloud, okay, which is a neighboring galaxy to ours. And then we are looking at that particular source, and then we get absorption lines. And we are interested in this O6 line, which is present at about 1032 angstroms. So O6 lines are here and also here, but here it is very crowded. It's crowded in the sense that we have several other ions which are giving lines. So it will be crowded and it will be difficult to measure the correct, extracting correct information will be difficult. So we chose this one. Okay. So you can see two peaks for O6. Why do we get two peaks? Any idea? The source is in the large magnetic cloud. So the absorbing material will be there. Yes. So we have the absorbing material present in the Milky Way, and we also have the absorbing material present in the Large Magellanic Cloud. And because the Large Magellanic Cloud is about, say, 50 kiloparsec from the Milky Way, so it will be separated. So the absorbing media in the galaxy is giving, so that is the line at 1032 angstrom, and the absorbing media that is in the Large Magellanic Cloud, LMC, will be slightly at a higher rate. Okay, will be slightly at a higher rate because it is far away from us. Okay, so we chose this line, and then what you have to do, the next step is to fit the continuum. So we did not fit the continuum for the whole thing. The whole thing, you have to fit it something like this, which is very complicated. So we extracted a very small part of the spectrum and we fitted the continuum in the neighborhood of the O6 line. Only in the neighborhood, you can see. Only, say, from 1027 angstroms to 1035 angstroms. We fitted the continuum like this, and then because here you can see this flux, and in order to plot optical depth, we have to fit the continuum and normalize it. So it is normalized. Now we have 1 and 0. When we have 1 and 0, then we can find the equivalent bit. Okay, so we can find the equivalent bit. What again we'll have to take care of this is there anything else which is absorbing at that particular wavelength? Is there anything else which is absorbing at that particular wavelength? So we found that there is H2 absorption, which is absorbing at that particular, 10 in the vicinity of 1032 and 1032, 1033. Okay, so we created a model spectra for H2 lines and we subtracted it from our lines. So this we have, you have to be very, very careful because you want to get good results, exact results. So you have to do this. You have to be very careful when you're looking at lines and where there is crowding, what is overlapping, all those kind of things have to be taken into account. So it was very good that O6, the number of O6 ions were larger compared to H2. So we can subtract it off. If H2 was larger, then we cannot subtract it off. It's gone. We cannot do anything. We cannot measure O6. Yes.
But that includes a different meaning.
See, if we have separation, so we have a star here, and in the vicinity of the star, we have media which is absorbing, and in the galaxy, we have media that is absorbing, and we have telescope which is measuring this. Okay, so this is closer to us. Okay, so this will come at exactly the same wavelength where we are expecting, but something which is farther from us will be slightly redshifted. Yeah, so it is redshifted. But you can also have blue shift sometimes when a galaxy is moving towards us. You can have blue shift, but in this case, it was redshift, and it is separated by a huge amount, 50 kiloparsec. The LMC distance is about 50 kiloparsec, and it was very good actually that we got two peaks, and two peaks resulted in two papers. So one we did for LMC, and then once you have done all this, H2 removal, continuum fitting, H2 removal, you have done most of the work, then you have to measure the column density for LMC, you get one paper, you have to measure the column density for the Milky Way, you get another. And that is what we did actually. So we got 2 papers of this. So then you can, I mean, this is the line. So this Milky Way is stronger here, the LMC one is fainter. Something like this, we use this formula to measure the column density. So this is basically optical depth. We have plotted the refined optical depth, and then we calculated the equivalent width. We checked whether it is following the linear pattern or not. So it is optically thin. It was following the linear pattern, and then we were able to measure the column density, and it came to about 10 to 14. While hydrogen column density will be around 10 to the 20, 10 to 21, so it is quite small. And then you can do several other things. So what we did, we compared it. So all the red circles you see are the column densities of O6 ion. Larger circle means the column density is higher in that particular region. This is only for the LMC. Milky Way is not included. Okay, and the smaller circle means that it is the column density is less. And we compared it with H alpha image. So H alpha image, wherever you see the dark, that means a lot of H alpha emission is taking place. Means it is H2 region or some young massive stars are there. Okay, and wherever it is less dark, H alpha emission is less. Okay. But we thought that we might find some correlation between the H alpha emission and the O6 ion column density, but we couldn't find any correlation. See, this is so flat. I mean, this is the column density of O6 ion and the H alpha surface brightness, and we didn't find anything. But I mean, we thought that if H alpha emission is strong, more ions will be created, but it was not so. So that it actually O6 is representing what? It is representing the in between something like warm ionized medium and hot ionized. So it is representing the warm hot ionized medium there. Okay, and that so the creation of O6 is not due to H alpha emission. It is not related. We also measured the same thing we did with X-ray surface brightness, and we thought that X-ray might be creating O6 ions, but that also didn't turn out to be as we thought. It also is not showing any kind of correlation. Now here we went to 30 Doradus. So 30 Doradus is a super bubble in the LMC. I can show you where it is somewhere here. 30 Doradus is somewhere here, and it has a star cluster known as R136, which has very young stars. There's a lot of young stars. So young stars will be emitting a lot of high energy photons. So we thought that let us move away from that cluster and let us see how the column density is varying as we move away from the cluster. When we move away from the cluster, then the number of high energy photons will be reduced. So luckily we got some small correlation. As we are moving away from the cluster, we find that it is slightly decreasing. The column density of O6 ion slightly decreasing. This was the lucky thing that we got. And we also got with the X-ray surface brightness. It is slightly increasing. As the X-ray surface brightness in the 30 Doradus in the same region, as the X-ray surface brightness is increasing, the column density is also increasing in the large magnetic cloud. So this was also, but only for this particular region. For the whole LMC, it is not true. For some particular regions, we can find some correlation, but mostly we do not have any correlation. So that's it. There's some super bubbles in the LMC. I think that is the end. Yeah. So I don't have any time. Tomorrow I'll have practice slide. So I think I'm done. And if you have any questions, I'm ready to take questions. Question from online. Yeah.
Like the diffuse level goes back to the staff. The diffuse level is coming from after the staff.
Yeah. Yes.
Yes. when those layers have more metallicity, it would be difficult. You won't have a lot of hydrogen. So how do you
See, hydrogen will always be highest because hydrogen is always everywhere it is present, and but metallicity will be higher when the star is releasing material. That means whatever star has produced due to the nuclear fusion reaction, it is all going away with that material. Okay, so metallicity will be higher, but metallicity doesn't mean that metallicity is what metallicity. It is a number in comparison to say hydrogen number density or some other material, carbon number density also sometimes oxygen number density. And compared to hydrogen, it will be very less. Metallicity, I mean, the number of atoms, heavier atoms that are produced will be much, much less than. But it will have higher metallicity. So, metallicity means heavier elements, how much heavier elements are present. So, if it has higher metallicity, then that means that more number of heavier elements are present, more amount of heavier metals are present there. And lower metallicity means that number is less. For example, LMC, there is another galaxy, neighboring galaxy, which is known as small magnetic cloud. So if you compare small magnetic, tomorrow I'll show you. So small magnetic cloud, and you compare with large magnetic cloud and our galaxy, what we see, we are surprised to see that small magnetic cloud has lower metallicity, has much lower metallicity compared to LMC and the Milky. So that what does it signify means maybe the stellar evolution is slow there, it is not taking place. I don't know. It is difficult to understand. We're trying to understand that. But this is a surprising effect. So the galaxies that were formed early, just after the Big Bang, those had lower metallicity. But then stellar evolution took place, a lot of stars formed, and then they evolved, they ejected material. So the galaxy that we see in current era has higher metallicity compared to those metallicity because of the evolution. So metallicity doesn't tell you that, for example, carbon is more than that. Can never be. But metallicity tells you that carbon here, this particular environment is higher compared to this particular environment. If this has higher metallicity.
generally the composition will show that the same even in different kinds of galaxy like spiral or
No, it should change. So the amount of, say, for example, molecular clouds, it will vary. Maybe in elliptical galaxies, those are less in number. Milky Way it is much higher. That will vary. It is not like fixed for everything. No, it varies. Any question from online audience? Any other question? The online audience?
There doesn't seem to be any questions.
There are no questions? Okay then. Thank you very much. I'll see you tomorrow. Same time.
Yes.